I'm Leo Holberg from the physics department here at Stanford and part of the Stanford Center Position Navigation Time. First thing I want to do is thank all of you for taking time from your busy schedules to come and join us at this meeting. It's greatly appreciated. Your input and feedback of what the center could be doing and which things are of interest out in the real world is valuable to us, so feedback would be great. It's my pleasure now to introduce Geoff Blewitt. He's currently professor at University of Nevada, Reno, and he has established a laboratory there that's called the Nevada Geodetic Laboratory, professor of geosciences. His work there involves integrating signals from 15,000 geodetic sensors and very impressive results that he gets. It's a little bit frustrating to me. I think often that lasers are the right way to measure precise distances and range and optics. We saw how hard it was even to measure in the buildings with cameras. The measurements they're making are at the millimeter level over hundreds of kilometers. This is parts in 10 to the 8 or parts in 10 to the 9. That's extremely hard to do even in a laboratory environment with stable temperatures. And that's done with radio frequency, so it's an inspirational work to me that Geoff and his colleagues have been doing. He did his PhD at Caltech some years ago. You may recognize one of his thesis advisors was Richard Feynman. Geoff spans from physics. He's won awards for detection of neutrinos from supernova. He's won awards from European Geosciences Union for geodetic theory, advancing global positioning systems for scientific research and applications, and for outstanding contributions in applying geodesy to geophysical and climate processes. Please join me in welcoming Geoff Blewitt to the stage.
I'd just like to acknowledge my colleagues here, Bill Hammond and Corne Kramer, both professors with me at UNR. And we do have a website that shows the results from all the 15,000 stations that we process, some of which we process within an hour or two. The rest we process within about a week and make the results publicly available at this website right here. The end product of what I'm going to talk about today is shown on the right, so I'm not going to describe that now, except to point out that this is a map of uplift in millimeters per year, ranging from -3 to +3 millimeters per year in the western United States. And there's some very interesting geophysical features there that we didn't know about until we were able to come up with an image like this. I feel like I need to introduce geodesy since this is a slightly different audience that I usually talk to. I attend like the American Geophysical Union and the International Association of Geodesy conferences. Geodesy is the science of Earth's changing shape, its changing gravity field, and its changing orientation in space. And obviously through the physics of the Earth, all of those three things are connected. And what you can see here are some images of the various techniques, starting with lunar laser ranging in 1969. And then you have the LAGEOS satellite, which is basically like a big disco ball from which you can reflect laser beams. And that's the best method for determining where the center of mass of the Earth is. And we can measure where the center of mass of the Earth is with respect to its surface with a drift of better than 1 millimeter per year. In fact, it's just a few tenths of a millimeter per year. Then we have the VLBI techniques, and this is actually me with Larry Young back in the 1980s when we were first testing out the new choke ring antennas, and we actually tried to put it to a practical use to measure uplift at Mammoth, volcanic uplift at Mammoth. And this is at Owens Valley Radio Observatory. We were using this as a reference point. So we knew the position of the radio telescope, and that's how we were using the reference point. NASA in the 1980s put a lot of money into high-precision geodesy using GPS in order to directly test the theory of plate tectonics. So that infused a lot of funding to generate the kind of equipment that we needed and the software that we needed. And developing the software was my task. So what I'm going to present here, this was 30 years ago. So I'm going to present my perspective over the last 30 years, just because everything is exponential. And I just thought you'd be interested to see how the exponential changes has occurred in geodesy. And of course, I would be foolish to try to predict the future. It's based on the past. It's not very predictable, in my opinion. So I'm just going to present the way things have changed. And of course, everything is exponentially, and you can see it everywhere, including on supermarket shelves, for example. Okay. So this is how things looked 30 years ago. My first job was actually to go out with Ruth Nealon. If some of you know Ruth Nealon, working with the International GNSS Service. At the time, we did field work in this Series X receiver. So this is the GPS receiver right here. We were trying to gather some data and then use that data in software that hadn't been written yet, and then attempt to come up with a similar answer to VLBI. So we were attempting to replicate the baseline between Owens Valley Radio Observatory and the radio telescope at Mojave, the Goldstone antenna. And actually, after a couple of years, we managed to get agreement to within about 10 centimeters. But by 1990, we were getting good enough measurements, and we were starting to use commercial receivers at that point, that we could actually detect for the first time the movement of the Pacific tectonic plate with respect to the North American plate in California. That was quite a milestone. Modern GPS geodetic stations are quite a different beast than the kind of GPS stations you might be familiar with. For one thing, they are connected to the ground typically at 10 to 15 meters depth, and then are uncoupled from the ground from that point upwards, so that they're immune to the freeze-thaw cycle and any fracturing that occurs at the Earth's surface and weathering and so on. Then they typically have a radome covering a choke ring antenna. And also, of course, they're dual frequency to calibrate for the ionosphere. These are the only kind of stations we really look at, well, at least the dual frequency stations. As for monumentation, that's how deep are they anchored. That's a different story. We instead, as I'll explain, use robust estimation techniques to weed out the stations that don't seem to be fitting the behavior of neighboring stations. But the number of GPS data has doubled every 3 years, and funnily enough, it starts with one receiver in 1973, which is an interesting coincidence. So this is what I call Blewitt's law. You can write an exponential in many ways, and this is one way. So 2 to the power t minus 1973 divided by 3. So this is, of course, when the authorization was given to go ahead with Navstar. You can see the distribution of stations is highly inhomogeneous around the world, and that's just something we have to live with. This comes from an NRC report in 2010, and it shows the various applications in geodesy as plotted as a function of precision on the left and time scale on the bottom. And the number of applications has just exploded over the last 30 years. And I've been involved in some of these applications. Some of the recent examples include tsunami warning, where we look at motion of stations on land that get affected by the earthquake. We then invert for how big the earthquake was, which can be a problem for seismology if the earthquake's really large. Then we invert for how much the seafloor moved, and then predict what the tsunami magnitude is going to be. I've also worked on the extreme right side of this, where it demands stability at the level of 1 millimeter over decades to look at global sea level change with respect to center of mass of the Earth. Also looked at seismic hazard, geodynamics, and interestingly, hydrology is becoming important. So these are some of the events that have occurred over the last 30 years, which have actually been critical in order for us to produce the kind of images that I showed you at the beginning. Obviously, the invention of double differencing and applying that to carrier phase measurements by Chuck Councilman and others in the early 1980s was critical. 1984, it was kind of a milestone in highly precise GPS orbit determination using stations. There were known locations determined from VLBI measurements. 1986, we managed to get a handle on the time variation in the troposphere and its a random walk kind of nature from turbulence. And we're able to estimate the troposphere accurately in order to improve the vertical component. And also we started to estimate the clocks rather than simply double difference them. In 1989, we solved the problem of carrier phase ambiguity resolution over thousands of kilometers, and we could also completely automate the data processing. By 1992, we didn't rely on VLBI anymore. We could actually solve for all of the stations and the satellite orbits at the same time and produce an independent reference frame that could then be used to check against VLBI for accuracy, and then start to contribute to the reference frame in an independent way. In 1994, well, we think of that as the year when GPS became official, but it was also the year in which the International GPS Service started to produce a global analysis through cooperation of a large number of analysis centers around the world. And by that competition that occurred, what we saw was a rapid improvement in the products coming in the orbit accuracy and positioning accuracy. And also it fostered this international collaboration where the best of the best were working in different parts of the models and gradually improved the standards of the International Earth Rotation Service. 1997 was quite a milestone year. At JPL, precise point positioning was invented using carrier phase, and shortly after that, the precise point positioning with ambiguity resolution, which enabled us to, for the first time, analyze all of the stations in the world with at a processing time that went linear with the number of stations, which was really an important breakthrough to make. So each station could be analyzed independently. And then there was a number of improvements in Earth motion models, in antenna calibrations. Satellite laser ranging to GPS satellites was really important to the whole problem of calibrating the scale of GPS. And then global ambiguity resolution for precise point positioning in 2008. These are just to name a few of the breakthroughs that occurred. And this just shows what difference 2 years can make. This is a station in Nevada called Elko, and this is the vertical time series as a function of time produced in 2010, and there's the same time series produced in 2012 with improved models. And this is the kind of improvement that we just see every 2 or 3 years. If you look at stations in stable plate interiors, you can actually come up with an estimate of accuracy on the assumption that the plate interior is not deforming. And what we see in North America is the accuracy is now at the level of 0.2 to 0.3 millimeters per year in the horizontal component, and maybe 0.5 millimeters per year in the up component. Now we're looking at all the stations we can possibly discover on the internet. And this just shows a small portion of that in western United States. It may look a little unfamiliar to you because the orientation is such that it up and down is the boundary between the Pacific and North American plates. But you can sort of see the outline of Nevada there, so it kind of gives you a georeference. This, of course, is the San Andreas Fault with a huge variation in velocity as you go across that. And if you plot that variation in velocity, that's what we call strain, so that's the gradient of velocity. You see this kind of a pattern, and what you discover is that the San Andreas Fault is not the only player here. You've also got significant strain on the east side of the Sierra Nevada, which acts like a cold, solid, rigid block. And the hypothesis is that this is really where the plate boundary wants to go, and it's slowly moving its way northward. And you can trace it back to what's happened in Baja California, where there's where the seafloor is spreading apart, and eventually the seafloor spreading apart will come up through this side of the Sierra Nevada and form the new plate boundary. So that's the current hypothesis of what's happening. We can do these kind of maps all over the world, and this comes from a wonderful publication by my colleague Connie Kramer. It's about 40 pages long, and it's such a beautiful paper to look at the images. But you can see all kinds of detail in strain in the Earth, such as the uplift of the Himalaya, where the uplift has been so high that the Earth can't withstand the amount of pressure and is flowing, and those blocks of Earth's crust are moving away from the high topography. And you can also see through these hot colors where the strain rates are largest and where large earthquakes has the potential for large earthquakes. And you can see why Japan suffers so much right there. These kind of maps can be converted into probability of earthquake occurrence above certain magnitude, which can feed into earthquake hazard assessment planning. We can't, unfortunately, tell when earthquakes will occur, but at least we can say where they're most likely to occur. We can now use GPS to image uplift. So I've been showing you mainly horizontal motions. And what's shown on the left here is uplift across North America, where blue is down and red is up. And interestingly, Canada is red and the United States is blue. There's a physical reason for that I'll get to a little bit later on. And if you apply some of our imaging techniques, this is the kind of imaging that you get for uplift in North America. Again, the scale is from -3 millimeters per year to +3 millimeters per year. So now I'm going to explain how we do that image processing, and it involves some innovative statistics, like I'm showing here. So maybe it's not as egregious as that. So basically, we're taking GPS station data, we're processing it to produce coordinate time series for each individual station. And then for each individual station, we get a velocity. And I'll explain in a second, but that velocity is very robust, and it doesn't require human intervention. Then we get, we use the fact that stations that are nearby ought to be seeing something similar to get robust station network velocities. And then we come up with a final interpolated image. So the key to the robustness here is median filtering. And the first step is to do median filtering in the temporal domain in order to get a robust velocity for each station. The way that we do that is that we choose pairs of data that are separated by 365 days, and that's because GPS data are affected by seasonal signals, and then take the median of those differences. One thing that you might not be aware of is that GPS time series, when you're looking at highly precise data like this, are subject to step functions. that occur when antennas fail and you replace them, or even if you just replace a receiver with a different receiver that might have a different gain at different elevation angles, and so maybe seeing satellites all of a sudden in places that it never used to be able to see. And you can get step functions when you have equipment changes like that. You can also get step functions from intentional relocation of antennas, and sometimes they tell you and sometimes they don't. And sometimes you can get step functions from earthquakes. And we've come up with a technique that's insensitive to those step functions, and that's basically this very simple algorithm turns out to be insensitive to step functions. Then in the spatial domain, we look at nearest neighbors on the Delaunay triangulation. So typically you've got about 5 nearest neighbors to any point on this triangulation. And then you basically just replace the value of each point in the triangulation with the median of the neighbors plus yourself. This despeckles the image and is robust to outliers. But it's got the nice property that it preserves linear boundaries between domains. And this is the kind of processing that is actually used in photography. This is a bit of a technical slide, but it shows something interesting because I would challenge you to try to come up with the best trend yourself by eye to these black triangles. What I've done is I've inserted a step function which is actually here, where you see these gray points. That's the original data, and then I've added a step function at this point, and then the data continue with the same trend. Now, to the eye, you might fit that reddish kind of slope, and actually that is the least squares fit to the data. But the truth is the gray line, if the step function's not there, our algorithm comes up with this green line, so it's very close to the actual truth. Looking by eye, you might think that the step's actually there, but it isn't. So you might put in too many steps if you were an analyst, and this is what we used to do, was scan every single time series and try to insert the best steps that the eye could see. And when you detrend the data, you find that you can interpret it much easier. So here's an example of an earthquake that occurs near Reno, so it's near to where I live, where an earthquake occurs, but interestingly this step here is not the earthquake. It's just that the station continues to move for several weeks afterwards without very much seismic activity. It's sort of a seismic slip on the fault. So that was quite a discovery. But as far as this algorithm called Midas is concerned, it did accurately fit the trend before the earthquake very accurately by taking the median. Whereas if you took a least squares fit, it would have somehow went through the whole thing, and it would have been a little difficult to interpret. Second example is a station with an equipment change that was undocumented. So we managed to get the slope correct there by eye. And the third example was an intentional relocation of a station that got vandalized. And you see we're totally insensitive to the fact that it's being displaced by 80 millimeters at this point. So we subjected our velocities to a fake data set that only some group in France has access to, and they inserted step functions at known locations. And we compared ourselves to 20 other algorithms around the world, some of which involved human intervention. And our algorithm turned out to be the most accurate. The accuracy we get, our accuracy is in tenths of a millimeter per year. So this is a 50 percentile kind of box, and that's 90 percentile on the outside. Then we compared ourselves with the best human analysts we could find, doing least squares and inserting steps. And we produce very similar maps fully automatically without all the time-consuming effort of looking at all these time series here on the left. The automatic results are shown on the right and visually look very close. Then we apply the despeckling algorithm. So this shows what happens if you apply a despeckling algorithm to an actual photograph. It's amazing how you can see the texture of hair coming through when it's not immediately apparent on the left. And this is the same kind of algorithm being applied here to the GPS data. So we're replacing each value with the median of its neighbors. And we actually use, it's a bit more complicated. We use what we call a weighted median. And then we finally interpolate the results, and this is the image that we get. So there's all kinds of interesting information here. It's a bit of a gold mine for the geosciences. This was just produced. This paper was published a couple of weeks ago and is available online. It's open access. Of course, we know the Great Valley in California is subsiding due to reservoir compaction. But the interesting thing is, because of all that loss of mass, there's less pressure on the Earth's crust. And given that there's less pressure on the Earth's crust rebounding upwards around the Great Valley. So the Sierra Nevada are moving upwards about 1 to 2 millimeters per year. And that was our models of Earth's elastic response confirm that that's in the right order of magnitude. What's a little bit of a surprise, though, is that there's a sharp edge between red and blue here. And actually that does correspond quite closely to where the active faults are up against the range front of the Sierra Nevada. So it seems like the hydrological signal, the hydrological forcing, is somehow being amplified or affected by the weakness in the Earth's crust at that fault. So there's some interplay here between tectonics and hydrology that's interesting. There's a lot of other interesting features here too. One of the main reasons for our deployment of many hundreds of stations in Nevada is to image this feature that we knew should exist. This area of uplift is Earth's viscoelastic response to earthquakes that have occurred over the last 100 years. There have been about 6 magnitude 7 earthquakes in this area, and our models predicted we should see significant uplift at the level of 1 to 2 millimeters per year. And that's what we see. So that's kind of confirmation of our models. You can also see where the tectonics transition from strike-slip faults to a subduction zone, where really massive earthquakes can occur in this red zone here, in the zone we call Cascadia. So they could easily be magnitude 8 and above earthquakes in that area from that strain accumulation. And if you're sharp-eyed, you might see Lake Mead here, which has suffered a lot of mass loss from water. If you go there, you see all the bathtub rings as the water's really depleted rapidly. We can also play the game of looking at time variation. It's a little bit difficult because the number of stations has been increasing exponentially. So it's sometimes difficult to interpret time variation. But the evidence does suggest that the most rapid uplift has occurred in the last few years and during the time of the drought in California. And the time series do show that nonlinearity as well. It's not just these images here. And then I get back to looking at this map of North America because it's got so many interesting features over many different scales. So far, we've just been looking at this small area over here on the west coast. But the dominant feature is this huge area of uplift and subsidence. And what we're imaging here is mantle flow. So the Earth's mantle is flowing because in the last ice age, the ice melted and sort of relieved the Earth of that load. And then the mantle wants to flow back under the Earth's lithosphere, which is elastically rebounding. And so the mantle is flowing from the US basically into Canada. And that's why the Great Lakes are there. So that's no coincidence that the boundary between the US and Canada is exactly between the red and the blue. Yeah. So that's, that resolution of the so-called hinge line of glacial isostatic adjustment is critical for modeling, correct modeling of where the ice sheet was, and it helps guide the people who do those kind of ice age studies to improve their models of the last ice age. One of the consequences of this is that the whole East Coast is subsiding, and it's subsiding at a rate which is similar to sea level rise, so it's effectively doubling the rate of sea level rise. So as each year passes and we get more, hurricanes and storm surges, the effect of those storm surges is going to be enhanced with time. On the smaller scale, we can also see delta processes and subsidence around Louisiana and Houston, and also to do with oil extraction as well. So GPS imaging has got a lot of applications that we don't yet know. I mean, it's a brand new technique, and just looking at the last meeting of the American Geophysical Union, we submitted some papers, but there were papers by others too. So there's, we have a concept of plug-and-play GPS, where we say we're willing to process anybody's GPS data anywhere in the world. Just make sure you give us the correct metadata, and we'll do all the processing all the way through to images, and of course the time series. So trying to lower the barrier to people installing GPS stations. There's the effect of the California drought on Sierra Nevada uplift. That was published recently. The reference frame is important, so we can now look to see if reference frame site velocities are regionally representative, and we're using this median spatial filtering technique. We can look at coastline land motion, its effect on sea level, and of course glacial isostatic adjustment. So this is just touching what's possible here. One paper that I'm a co-author on in the 2016 meeting is a search for dark matter from the GPS-DM observatory. So this is actually looking at the patterns that you see, or we hope to see, in the GPS atomic clocks on board the satellites. And we're trying to image how if there are patterns, spatiotemporal patterns in there that provide evidence for certain forms of dark matter. So in conclusion, precision GPS geodesy leverages off the success of VLBI and SLR, and I have to say we benefit a lot from the lessons learned from those techniques, which are strongest. Those techniques are strongest for various reasons. Like satellite laser ranging has got very easy dynamics to model of the satellites. So we can get a better scale from SLR and also a better model for where the Earth's center of mass is. And look at time variation in the gravity field too at the low degrees. VLBI is very good at, of course, doesn't have to worry about orbits. And so they can focus more on the tropospheric modeling, and anything that they learn immediately transfers to us because the tropospheric delay is exactly the same at the GPS frequencies. So we benefit a lot from their research. So this gives us access to millimeter position. It gives anybody access to it through the Plug and Play project. And it also inherently gives us access to this 0.1. In fact, it's better than 0.1 nanosecond timing. It's now tens of picoseconds. The growth is exponential in geodesy in terms of number of stations and data, and now in all the satellite systems coming online. The innovations in the algorithms and observable modeling continue, and the scientific applications are exploding. This leads to new scientific possibilities. We have GPS imaging now as a tool, which other people can now use for their investigations, and we can start to look at time variation. There's some very interesting work that I'm involved with CoPI, looking at, for example, at the effect of the Earth's response to Hurricane Sandy when it came onshore, and how the storm surge actually forced the Earth into a very slow biowave, which is a new kind of wave that hasn't been observed in the Earth before. It's a wave that you expect to see in a poroelastic medium. We're using it to look for dark matter, and I just have to say that future applications are too difficult to predict, and I wouldn't want to stick my neck out. But I do know, based on looking back at the last 30 years, that I should expect the new applications to be amazing and to continue to grow. So that's the conclusion of my talk. Thanks.
Time for a few questions.
Yeah, very interesting. I guess the question has to do with the relationship between what you're seeing in aquifers. Maybe you covered this and I missed it, but I seem to recall reading about satellite motion being used to measure that kind of hydrology. I was wondering what the distinctions are.
So there was a paper from UC Irvine on using gravity from space to measure how much mass had come out of the ground in California. So this is using the GRACE mission, where they're measuring the distance between two satellites in space and can infer the time variation in the gravity field. So they came up with an estimate of how many, what the mass loss was, but it's with relatively low spatial resolution, just by the nature of how it works. What we did was we inverted, our model is quite different, of course. It's all geometric, and we have to infer that there was some, through the Earth's elasticity, how much mass had been taken out. But it turned out that we came up with the same number within the error bars. But we do have an image of it, which is not something you can do from space, because the inherent problem of inverting gravity as you go downwards is it doesn't let you do that. But we have a very nice, crisp image of what's happening. So they're both complementary, I think, and important. It's important to use them together. In fact, the ratio of what you see in GRACE versus GPS is a function of actually the rheology of the Earth. Is it purely elastic, or does it have a viscous component? So looking at it from both aspects is really important.
So, sorry.
Yeah.
Okay, so you're talking about a few millimeters per year of motion.
Yeah.
At that level, how do you know it's not, if it's not something else? For example, if the antenna, thermal deformation, and many other things can give you that kind of motion, probably even more, right, over the time. How can you tell it's actually just a motion of the Earth?
So you're talking about if there's something, say, a problem with an antenna or something like that?
I'm just saying, because the temperature change, right, the antenna itself will experience thermal deformation. It actually
Thermal expansion, you mean? The thermal expansion is actually very, very small. It wouldn't be important. There are some parts. There are some locations where you can get thermal expansion that's important. If you're, say, on the edge of a cliff, and you have a free surface that can expand like that. What we've done here is we've tried to use the median spatial filter to help weed out problem stations. There might be just local artifacts like that. And actually, a bigger problem is failing antennas. They can cause drifts before they get replaced.
that may become typically very obvious, right? It's very detectable, but I can imagine very minor thermal deformations, which is coupled with the temperature. Canada, for example, is much colder, right?
Yeah.
Then, it's same type of effect, same type of global effect. Then it's hard to tell whether it's actually Earth motion or something else, which are also correlated with,
Well, it's very
geographically
true.
correlated.
We can't really, with confidence, in most cases, say what's the cause of seasonal variation.
Right.
Some of it may be temperature. Some of it's going to be actual loading. How much water is in the ground is very seasonally as well.
Right.
Maybe there's some systematic mismodeling of the troposphere that's seasonal. That's true. But some of the seasonal signals are certainly much bigger. There's orders of magnitude variation in seasonal signals, and when they're large, then you can really interpret them. I'd say above about 2 millimeters per year, you can start. 2 millimeters amplitude, you can start to interpret them as being real.
One more question here.
Yeah, Geoff, very interesting, especially that this has been accomplished with basic. It's not working.
Ken, turn your up.
Okay. Yeah, this is doubly impressive because this has been achieved in the past 30 years with actually processed data, process, carrier, phase, and code.
Yes.
So last year I'm on a committee of the European Space Agency, and what I propose is that we start considering storing permanently I's and Q's data in order to benefit from processing methods that have not yet been invented. Of course, the big disadvantage of that is immense storage space. However, given applications that are not yet defined, such as dark matter, that I didn't know that you were looking at that, I think there might be something in those I's and Q's, some signals that we cannot recapture with code and carrier.
Yeah,
So it looks like that
yeah.
might be an interesting way to the future.
I'm all in favor of saving as much data as you possibly can. It's a practical issue, right? In fact, for the studies that we're looking at here, we're looking at slow variations, of course. That's our particular interest. And so when we look at slow variations, we only need to look at data every 5 minutes to get results like this. But there may be applications where it's really important to go to very high rates. I'm in favor of it. It's just a technical issue, right, to save all of that data. Yeah.
Okay, thank you very much.